Hey, okay, welcome back here to experiment number 2. I think I told you, and I kind of want to repeat it here, that the way we're going to do our labs this semester, because we're doing them remotely, is I'm going to kind of be your hands, and you and I are going to be the lab partner, and so I'll kind of do the equipment, and you hopefully kind of see what's going on. You're going to do some of the graphs, and this one has some really I'll call it advanced graphs. I don't know if I want to quite go that far, but they are more advanced than the ones we did in the first week. So I'm going to show you some more about graphical analysis, and probably less and less show you graphical analysis as the semester goes along. But I will say that if this goes well, and if the other one went well, I'll be sending this out to you on the Sunday of the second week. Actually, we got done filming about 2 hours ago the first lab, and I was gonna wait for some feedback from you guys if it was going okay, and I just got to thinking, you know, it'd be nice just to do the second lab. So we're still in the lab. It's still the Monday of the first week, and I'm just gonna make this second one right away. I kind of like that idea. Even though I did look at my email real quick while I was getting a bite to eat, and noticed that on this first day, a lot of you have sent me a bunch of emails. So I really probably need to get on that. I suspect some people are adding for ad codes, or maybe have some questions on the stuff I sent you on Sunday. Anyways, I will get that to tonight. So you probably will hear from me if you sent me an email tonight, Monday night. But anyways, let me just see if we can get this one going. And I'm going to say the same thing again, is that you need to put all this together in a PDF file and send it to Canvas sometime during the second week. You'll get this a link to the video Sunday at the start of the second week, and you have all week to do it, and you got to turn it in by Sunday night of the second week. And so this particular lab is on the next chapter, chapter 16. And so when I send this out, I will also be sending out chapter 16. So I'm going to say the same thing like I said in the first one. Let me encourage you to get started with chapter 16 before you do the lab. You don't have to complete chapter 16, but you should have at least read through chapter 16 the first time, like I'll always say when we start a new chapter. Then I think you should watch the video lectures on chapter 16. And then I always say read it a second time for full understanding. That you may want to do the lab before you read it fully a second time, or maybe you should just read it a full second time. But I should probably just say that. Read chapter 16 a full second time. And then as you start doing the problems, you can either do the lab first or the problems first. The problems will take you a while, so you know, maybe do one or two, take a break from that and come over to the lab or something like that. But certainly you don't need to worry about doing all of the problems from chapter 16 before you do the lab. That's for sure, because the problem from 16 may take you a few days working through that. And actually doing the lab hopefully will be a help to your learning process. And so sometimes it's, you know, better to mix back and forth, because hopefully what we do in the lab and what you're doing as the homework problems, you know, couple with each other. But like I said, you really need to understand the basic idea of the waves of chapter 16. So again, make sure you've at least read chapter 16 once, and you've at least done the video lectures once before you start the lab. And it couldn't hurt to have read the chapter 16 a second time. So I'm going to begin by saying chapter 16, you learned something really important in section 3 of chapter 16. And it doesn't matter whether you're in the Survey book or the OpenStax book. In chapter 16, section 3, your author or authors derive the velocity of waves on a string. And so grab your PDF lab manual, and so here it is again. I'll hold it up here. This is the hard copy one, and again, you don't need the hard copy one because everything you're ultimately going to be turning in is going to be a PDF anyways. But turn to page 6, and so here's my page 6, and so here at page 6, you will see the title says string waves. So we're going to make some waves on a string. Now let me put an equation on the board. Let me come all the way over here to the beginning of the board and put a very important derived equation that I will even say, and you'll hear this when you go through the video lecture, that I did not take the time to derive this equation. Your authors do a good job. In fact, the survey author does it twice. He derives this equation first in section 3, using kind of a circular motion method. He derives it again using calculus in section 7, I believe. Might be section 6, but it's the last section of 16. I believe it's section 7. Now, the author of the OpenStax, or I should say authors of the OpenStax, actually derived this equation also in section 3, and they only use the calculus method. They don't use the circular method, and they come up with this equation. Although maybe I'll put here for the OpenStax book, they put F sub t over mu. Now, the T is for tension in the survey book, and the F sub T is the force from the tension. And so maybe I should just spell out then that the tension on the string is what's in the numerator, and the denominator is what we call the mass density. I won't write density, I'll just say mass per length. And so how much does the string weigh per length? So without deriving this equation, but starting the lab here today with this, let's perform a little experiment like you saw in the first one, and you'll see throughout this semester, is we want to test this equation. We want to see if this equation is valid. And in the process of testing this equation and seeing if it is valid, we will be able to measure things. For one thing, we will get, when this is all done, after we collect a bunch of data, besides that we will verify that this equation is correct, we will then get the mass density of that. Okay, and so again, just like you saw in the first experiment where we did this graphical analysis, and then we plotted it, and then we made a plot with some complex axis to make a simple graph, and then we use that simple graph like the slope and the intercept to get some data. We're going to do exactly those same lines, and so that's the part of the laboratory technique that you're learning in terms of the graph, that we're learning how to do a graph, okay, and the value of getting data from a graph here. All right, so I think for our discussion, I'll use the notation from the survey book for T for tension here. But what we're going to see then and collect basically is I will change the tension. So we will measure the tension in newtons eventually. And we will see how it affects the velocity. And so that's kind of the big picture here. Okay, but let me give you another equation from, again, chapter 16. And I believe this is section 1. It could be 2. But as he works through the wave equation, he introduces you to the wavelength. And so this is the distance that it repeats itself. And he introduces you to the frequency. Now, frequency is something we did back in chapter 15 before we even had waves. We just had oscillation. So there's nothing new about that. But that would be the rate at which the string goes up and down every second. But let me highlight this equation. Actually, maybe I'll highlight both of them. But this is ultimately how we're going to get the velocity. So what we're going to be measuring is the wavelength and the frequency. And in a moment when I start to set up the equipment, you will see, and I will point out, that we're going to put our little oscillator and plug it into the wall. And for the half of you out there who've already gone through Physics 122, you will know that we had said numerous times last semester in 122 that the rate at which the current changes in a wall plug in North America is 60 hertz. So what I'm going to do is build a little oscillator and use the electromagnetic effect of the current that's in the wall, and of course since we're here in North America, it will then oscillate 60 times a second. So know that for our little waves we're about to create, the frequency will always be 60. I can't change that. Again, maybe you guys remember from that oscilloscope lab where we did the Elisaju figures for those of you in 122, and we were trying to compare the oscillator that we could change to the wall plug, which we knew was at 60. All right, so I'm going to just need to tell that to everybody just in case some of you forgot, and a lot of you, half of you, haven't even done that in 122. You'll do that next fall. So you need to know that. So in reality, what we're going to be measuring is the wavelength, and from that get the frequency. Now, let me put another equation up here, one from your Physics 121 class, and one we actually used last week also. That is, if you're hanging a weight, its weight is mg. It's mass times the acceleration due to gravity, 9.8. And so to put tension on this string, as you'll see in a moment, I'm going to just hang weights from it. So this is how we're going to get the tension. So again, we're not going to measure tension directly. What we'll do is we'll hang weights, then multiply it by g in order to get the tension. So let me put a big table here on the board, because what I'm going to actually measure here with you in a few minutes is the mass in kilograms that I am hanging, and also the wavelength in meters that result when I actually make the waves and make a measurement. So that's the raw data. And then I'll show you graphical analysis, because we need to get to tension and velocity. So we will make a new calculated column, which is the tension in newtons. And so that will be a new column, and it'll be a calculated column. And it'll be just like we did last week. And I'll show you that one kind of quickly again, but it would be just to put in this formula. And then likewise, we would like to know the velocity in meters per second. And that would also be a new column. It'll be a new calculated column, because I'm going to get that by then multiplying the wavelength, which I'll directly measure, and then multiply it by the frequency of 60. So that's how I will get then the tension and the velocity. Now, let me put two more columns up here, because this will tie in to the second question of the first lab. Remember that second question of the first lab said, hey, what if you don't know the relationship between two things that you've measured? Now, I'll be very clear, we do know the relationship between tension and velocity. This is it. But your author says, if we didn't know it, do you remember that discussion about taking the log of each side? So you are going to be asked to plot then the log of the tension and the log of the velocity. And of course, if you kind of remember that discussion from the last lab, we learned that by taking a log, if you have something that's raised to a power, and you could think of this as tension raised to a power of 1/2, so you should get a straight line of a slope of 1/2. And that's what we're hopefully going to see. So this is what I meant earlier when I said, okay, we're going to use graphical analysis a little bit more, a lot more than we did in the first lab. But I need to build up to that. And so at this point, I just want to hook up our string waves and fill in this chart here for a given mass. What is the wavelength? Okay? And so let me jump over to the equipment and set it up and just taking some raw data. Although before I do that, I'm going to hold up a printout of page 7. And on your PDF, you can look on page 7. But on page 7, you will see that the first column says load, and it gives you the mass you're supposed to hook up. Now, granted, this mass is in grams. So when I type it into graphical analysis, I'm going to follow what I did up there. I'm going to type it in kilograms. And then it says what's the wavelength, and they give 3 columns. And the reason there are 3 columns is because you are asked to create waves on a string, but 3 different strings. And the difference between these strings is, and wait for it, come over here, the thickness of the string. That is its mass density. That is how much does it weigh per meter. In fact, I'll even show you the strings right now. They're down here in front. And the first one we're going to do, we will call this the light string. This is the kite string. And I'm kind of hoping maybe you can see on the video its kind of thickness. It's actually pretty light. This will be the medium one, but let me jump to the thicker string, the cotton one here. This one is much thicker and therefore has much more mass per length. And so we're going to do, this whole experiment really 3 times. And each time we're going to do it with a different string that has a different mass density. So again, hopefully by the end of the lab, we will get our point across, and that is that equation valid? That's the main point of the lab. And then along the way, hopefully we'll learn how to do some more graphical analysis, how to take a complex function and turn it into a straight line, because instead of having simple axes and a complex function, we'll have a complex axis, so we'll do the log of the tension and the log of the velocity, and we will have a simple equation. A simple graph. It'll be a line. And so all we'll measure is its slope and its intercept. But then once we get a slope and an intercept, we can use the slope and the intercept to draw the conclusions of the measured value. And one of those things will be what is the mass density. And another one will be what power is it raised to. Because remember, a log function, the slope is the power that it's raised to. And the intercept is related to the coefficient in front. And I guess I'll call it in front because that's how I derived it last lab, but this would be underneath it. But anyways, it's the coefficient out in front. Maybe the name prefactor would be a better description there. All right, so let's go through these. Now, I will put some parameters here. I'll just say it in words, but you can kind of see it. I already etched out some of the masses. For the light string, we're asked to do from 10 grams to 250 and not the heavier ones. And then the medium ones were kind of in between. Let's see, what did I mark? We're asked to go from 40 to 450 grams. And then for the heavy white cord, we're asked to start with 100 grams and go all the way to 600 grams. So there's a slightly different range. And since we're graphing that on the x-axis, I should say domain of what we will be plotting on the x-axis. And so because of that, I need to show you something very interesting and useful in graphical analysis of how do you plot 3 different plots on the same graph, and when their domain is slightly different. And did we do that? I don't know if we did that in 122, but whether we did it or not, I need to show you, because at least half of you are coming from 121 and you haven't used graphical analysis. So I need to show everybody here how you would do that in graphical analysis. So again, I will. But now let's get started with the lab. Let's actually start collecting data. Let me come around to the front so you can kind of see the experiment a little bit better. Oops, I bumped this. It's still on, Ron? Can you hear me? And let's do a sound check. Okay, good. And you guys then, and I'll again just kind of say the same thing. I'm your partner. Okay, so I'm going to make some measurements here. And you might see that I have a string laid out. And the string runs along my desk here. And then over here at the end, it goes over a pulley where I can hang weights. And I've started with just the hanger. And so I'll just tell you, because you wouldn't be able to see. Remember, I'm the partner with doing the hands-on stuff. But as I look at this, it says 50 grams. So right now, I am already set up for 50 grams. And I set it that way because even in a face-to-face students, I always tell everybody, hey, do the 50 grams first. Because less than 50 grams is actually pretty hard. I'm hoping I won't have too hard of trouble in front of you and embarrass myself. But it takes some experience, and I have that experience, so hopefully I won't struggle too long with it. But in a classroom setting, I know that I have to go around, especially get down to that lightweight of 10 grams and go, oh, here, let me help you with that, and sorry, that's just the best it's going to get. But I think it's best, and that's why I always tell students, and I'm going to tell you guys, let's start at the 50, because the 50 is an easy one. It's easy to do, it's easy to see, and it's a good place to start. So we'll start at 50 and get heavier, and then we'll go a little lighter, and we'll fill in for the light string. And by the way, this is the light string. So before I started the video, I laid out the light string here, and it's basically ready to go. Now, over here on this end, this thing right here is the oscillator. If I push on it, you can see how it is movable up and down. And there's a little electrical wire that goes back to plug in right here, and it goes to the wall. And so when I plug it together, it goes up and down. And it's going up and down 60 times a second. It doesn't go up very much, so I'm not sure if you can actually see it on the video, but it probably looks a little blurry. You might even be able to pick up on the mic. You might hear it going up and down 60 times a second. Sometimes to convince students, I'll put something like maybe the scissors on top. And you'll see it just slam into the scissors, and you'll hear it hit. And so it is going up and down. In fact, if you stand back now and look at the string, and I'm hoping this will come out somewhat decent on the video here, but you'll see these waves. Now let me turn it off for just a second and draw a picture here on the board. Because now that you see the equipment, let's just make our measurements. Let me draw a picture for you. This end over here is the oscillator that's going to go up and down. And before I plug it in, the string would just be straight across and level. Or close to being level. I know it weighs a little bit and gravity's going to pull it down. But it's pretty close to level. Let's just kind of ignore gravity in here. And so what's going to happen is we're going to get some waves here. Let me just draw a picture of what it might look like at some moment in time. Maybe the oscillator will be up about halfway. Maybe the wave will go up and it'll come back down and go up and come back down, and something maybe like that. And if you look closely at it, that is actually what's going on at that moment in time. But a moment later, maybe this is on its way down, so this is a little smaller. Oops, that was a bad drawing. It'll look like that. Maybe a little moment later, this oscillator has come down to here, and so it looks maybe like this. And so I'm going to draw a bunch of, I'll call it loops here. But I hope you get the idea of this picture. I am not trying to say the string looks like all of these at the same time. It only looks like one of them at one moment in time. Okay? And what's going to be really easy to see with our eyes are these points here that I'm going to call nodes. Now, sadly, your author doesn't start talking about these names until, well, for Survey, it's not until chapter 18, and in the OpenStax, it's in chapter 17, and starts to call these nodes. So let me introduce a new word to you. These are called nodes. You'll see them in week 3. But what I do want to point out, and so maybe I'll change colors so it stands out. Let me just pick out one moment in time. And so this red one is supposed to represent at one moment in time, and so I'll kind of mentally ignore the other ones for just a second. But as I said earlier on, I want to measure the wavelength. And since these nodes stand out and the tension makes the top of the pulley the node, I have set up the meter stick right at the edge of the pulley here. And I'm going to go out and go, okay, when I get to the first node, that's not quite a wavelength, right? That's half a wavelength. So then I'll go out to the next node, and that will be my wavelength. So those are the two things we're going to measure here together. So again, you and me, we're partners here. Okay, I'll do the hands-on stuff. You kind of look and learn, and then write down the data as I'm writing it down, so that we can fill in these two columns right here. So I will keep changing the amount of mass, and as I said, I'm going to start right about here at 50 grams. That's 0.05 kilograms, and that's going to be my starting point. And then I will turn it on, and with you, with the video camera, we'll look, and we'll go over to here, so that'll be a half wavelength, and then we'll go over a little bit more until we get a whole wavelength. Now, I must tell you, some of these wavelengths are huge. They're bigger than my table. So if I can't see this second node because it would be way over past my oscillator, I will just look for the first node and double it. Okay, so from the top of the pulley, which is the node, to the first node, remember, is a half wavelength. So if that's all I can measure, then I'll double it. But for the ones that I can see a whole wavelength, let's go to the second node from the top edge and just measure a full wavelength. So like I said, most of the time we'll be able to measure a full wavelength. But there are times where we only can get a half wavelength, so I brought the calculator out here, and I'll just double it. Okay, so that's the goal. All right, so now me come around to front here. Now that I think you kind of got the idea of what we're doing here, let me turn it back on. Let me just kind of double check that my meter stick is got a 0, or actually this is a 2 meter stick, but is at the top there, and that looks good. And that's the 0. I had to turn it upside down, so we're going to have to read the numbers upside down. But let's look for that first node and then the second node. And maybe if I get down low, you can see the string still, and I won't get into the way. But it looks like if I go across here, and it's kind of hard to see, even, and I'm, the camera, I don't know if it's easier or harder on the camera because Ron is telling me he's zooming in, and so maybe it's easier, but there is definitely the first node, and then right about here somewhere is the second node. And so it looks like it kind of tapers in, and I'm going to call that, how about a 92.8? 92.8. All right. So over here at 50 grams, I'll do the wavelength at 92.8 centimeters. So that would be 0.928 in meters. So I'll just put it in meters. And then later on when I type it in, I'll convert the grams into kilograms. All right, so let's go a little heavier. So that was the 50 grams. Let's go to the 100 grams. All right, so to get 100 grams, let me put on another 50. All right. And let's see what we get. So I'll come over here. Here's the first node. And let me keep coming. And it looks like in this area somewhere is the second node. And it doesn't come to a complete point, but let's see if I can get some symmetry. About 132. Oh, why not? So I'll call it 132.0. Move it 2 places, and that'd be 1.32 meters. All right. Let's go a little bit higher now. Let's go to 150. All right. Well, I don't have another 50, but why don't I do this? I'm going to take a 50 off and put on 100. So I have 100 and then the hanger, which is 50, and that makes a total of 150. Now this amplitude's kind of small. I might be able to get it a little better if I move this around a little bit. I think that's enough. Okay, and so let's see. It looks like it comes over and looks like there's a node somewhere in there. And then it comes across. And it looks like there's a node here. And maybe 158.2. And 158.2. Okay, let's go to the 200. All right, so coming back over here to the 200. Now I'll just put another 50 on this. And we might get too close to that oscillator. Now I might have to start doing a half wavelength. But you can see it kind of jumping around. It's a little unstable. So I'm going to see if I can stabilize it a little better. But not always so easy. As we start to get too heavy, let me try the other direction here. Okay, I think that's going to be stable enough to measure. It's got a big amplitude, and you can see it looks like way over here is that first node, and don't even get to the second node because the second node would just, because remember the oscillator is moving, so it would be just a little bit beyond the oscillator. So here's where I'm going to have to do half a wavelength and then double it. Okay, so best of my ability. Oh, it was a little more stable a second ago. But I'm going to take that as a 93.5. So 93.5 times 2 is 187. So 187 and 1.87 meters. Okay, and then the last one for this string, like I said, when you get to the edges, they get a little bit harder. Let's go 250. I think I got a 200 here. Good. And so I'll take off the 150 and put on the 200. And that's, again, I'll just go to the first node here because I can't get the second node. And maybe the first one is about 100 and maybe let's call it 103 and a half. 206, so 207. So 207. So 2.07. Nice. Okay, so those are the big ones. Let me do a little switch here and work downward now. Take all this apart. And let me put a smaller hanger. This hanger is 10 grams. And since that'll be the hardest one, let me work backwards. I'll go to 40. So down here, I should have a 20 and a 10. And so let me just put on a 40 here. And let me come back and see if I can get something a little more stable. Oh, like that. Let me grab my pen. Let me find that first node and then second node. And now got a little bit unstable. Okay. And so maybe right there, 82.8, so it's a little more unstable. Well, I'm gonna call it an 82.8. All right, so 82.8, and then move the decimal, and so 0.828. All right, let's go down to 30. So I'm going to take off a 10 here. And then read across. So there's a node. And here's the node. Okay, so maybe we'll call it a 72.2 and 72.2. All right. Let's go down to 20. So take this off and put on a 10. So the hanger's 10, I got a 10, that's a total of 20. First node, second node, right about there. Okay, 59.6 maybe? So let's call it a 59.6. All right, and so last one for this string. And definitely another hard one because it's the two extremes. See if we can get a little more stability. First, oh, okay, be nice. But somewhere like a 40.8, huh? I'm going to call it a 40.8. Why not? And so this will be 40.8. Yeah. Ta-da! Okay, so there's my first third of the data, and we're gonna put that into a graph. However, let's do these other ones here. All right, so I'm going to disconnect it, and so you can kind of see how this works. Let me just move the meter stick back. Let me take off this hanger. In fact, might as well just take off the string, it kind of weaves through this. Oh, now I got it all knotted up. So let me take it through that, and I'll just leave it tied on, and then I'll move over to this string. Okay, so this string, I'll just tie it on here, and for better and worse, this one is a slippery nylon. So let me just put a bunch of square knots in here because it has a tendency to vibrate itself off. Let me get myself enough string that would come over the top and a little extra room. Okay, so there's the little extra room. Let me feed it through the oscillator. Let me put it over and there's my medium string, and you can see the weight just kind of pulls it down. It's a little bit more, but on this one, that's why we're not going to do the lighter weights. The 10 grams just isn't enough to lift the string. And this one, what do you say? The lightest is a 40, okay? And then we go to bigger and lighter. But let me start a little bit more in the middle. Let me start at 100, because the two extremes are the hard ones, and I just want to start on something a little easier, if you will. So I'm going to go ahead and take the 50 and put it on. Let me just double check. That says 50, that says 50. Okay, so here's 100, and I'll just hook it in here and tighten it up. Okay, and let me just move the 2-meter stick a little bit closer and make sure it's at the top of the pulley. Okay, and so that's my 0. All right. Yeah, it's too bad we're not face to face. It's your turn to get on your knees and start scooting around. I'm too old for this. Oh, no. But, okay, so let's do this one, and I'll plug it in. And see what we get. Oh, this one's got a huge oscillation that it's hard to even see the first node. It looks like that would be 1 and 2 somewhere around here. Let's see if I can dampen it down a little bit so that it's not quite so big oscillations, and we can kind of see the note a little better. Yeah, maybe that's good. All right, let me just double check. Looks like that's 1 and that's 2. All right, so if I kind of meet in the middle, is that a 72, 2? Oh, why not? All right, so at the 100 grams, let's go 72, 2. Yeah. And let me go up. All right, so let's put 150 on here. See what it looks like. That might be enough to see. There's a 1, and then here's a 2. Yeah, maybe in the middle here at 87.6. So I'll go 87.6. All right. Let's go to the 200 now. I'm putting a 50 on here. And see if we've got to kind of tune it up. Oh, that looks good. So 1 and 2. Right here in the middle is about 101.6. So 101.6, move the decimal. So 1.016. Now let's go to 250. And so that's a 200 and a 50, so that's 250. kind of jumping around here. Okay, so let's see. So there's the first node, and here somewhere roughly is the, oops, I bumped it, second node. I'll call that 113.1, 113.1. Let's go to 300. So it's 250. Let me put a 50 on here. So there's 300. Okay, so there's node 1. And here's node 2. Okay, right there. Let's call that 24.3. 124. 124.3 with a little decimal. Okay, so that's 300. Let's go to 350 now. So take that 50 off, put on 100. So there's 350. So there's one node. And here's the second node, okay. So that one's really a pretty good one here. Let's call it 134.9. 134.9. Nice. Okay, that's 350. All right, so let's go to 400. 2, 3, 50, 400, but another 50 on here. So let's see, so that's the first node, and this must be the second node in here. So coming together, it's about 142.4. So 142.4 with the decimal. All right, and then the last of the big ones here, 450. Oh, I might have to grab another 200 here, 450. All right, so let's put two 200s and a 50. That's 450. Well, I guess the first node's somewhere in there, and then the second node, can't quite see it as well. Oh, let me put this back on now that we're starting to get some heavy weights on there. I'm starting to pull it. So maybe right in here, call it a 152.2, why not? 152.2. All right, so going the other direction. See if we can keep it from bouncing around, because this one is definitely going to be more unstable. Let me pull this back a little bit. Oh, I like that. So there's a node, and then there's the second node. Okay, so 50. I just lost it, but let me call it a 51.7. So 51.7. Okay. And then finally, the last one is a 40. This is where I'll need to change to the blue hanger. That's 10. And then find a 20 and a 10. Okay. So 30 added to 10 makes 40. And let's see if I can stabilize it a little bit. And so you can see why I did want to start with the lighter ones here. Okay, so there's one, and there's two, and so let's call it a 45.5, why not? So 45.5, nice. Yay! All right, so we're 2/3 done with the data. Oh, I think see it, yep. All right, and so there's the data for the medium one. And let me do the same thing. Let me disconnect the medium string and go to the last one, which is this white cord, and then give you an idea of what we talked about at the beginning, where the mass density would, change. Okay, so let me tie this on here. And say, okay. And this is another cotton one, so I don't think I need to do as many square knots. Won't shake loose. That's the good and bad about nylon, is it's really strong, but it's really slippery. If you don't get your knots well or burn them together, they come apart. Another interesting thing about nylon is I don't know if you've done your chemistry yet, but it dissolves in, it's made and dissolves in alcohol. But I'll never forget, we were water skiing one time, and we were out on the boat, and we were having lunch. We had skied that morning, decided to have lunch, and then after lunch, someone said, hey, I said, hey, yeah, I want to ski again. I said, all right, so I jump in the water and put on my ski, and they toss me the rope, and they pull the boat and tighten it up, and I say, hit it, and it pulls me, and I get about halfway out of the water, and the rope just snaps. And I just kind of sink back into the water, go, what the heck happened? So we circle around, we pull in the rope, we're looking at it, and I pull in my side, and I'm sitting in the water going, look, it just like broke in half. And like, whoa, we've just been using that. And then about 3 minutes later, I was like, yeah, but Robert, you spilt your beer. And you spilt it right on the rope. And so it dissolved the rope, but not completely, weakened it, and couldn't handle the stress. So sadly, our day of water skiing was over. We had no more rope, so bummer. But anyways, that was kind of an important part of nylon, and I'm sure you guys who do rock climbing know that. And, probably a little careful with your nylon ropes. Or I don't know, maybe you only use cotton ropes. Don't really know anything about rock climbing. Okay, but anyways, let me take this thicker cotton and pull it over here. And might as well put the kind of the middle of the road on here. Maybe 300 is the middle of the road. And so let me put is that a 50? Yeah. So a 200 and a 50 on here. So 250 plus the hanger is 300. All right, so we'll start there. And that's going to be a lot of tension. So let me come back over here and put this heavy weight back on here. Let me readjust the meter stick so that it's close, but hopefully not too close to touch the string and interfere with it. And let me just align it straight up and down so its 0 is right at the top of the pulley, so that's the node, and then we'll look for our wavelengths. All right. So let me turn this one on and see where we are. Okay, so it looks like one node. And here's 2 nodes. All right, so here's the second node. And maybe I'll come in here. Looks like that one's 137.4. 137.4 or 1.374 meters. All right, let me scoot over here and add a 50. I think I'll just take this 50 off and put 100 on. So there's 350. Let's see if that's stable. 1, 2, looks pretty stable. Is it a, and I think it's enough to see. Maybe we can do a little better. Well, maybe not. I'll just kind of do here and then come in the middle. Let's see how many. 1, 2, 3, 4, 5, 6, 7. So about 46. Yeah. I'll just call it a 146.2. 146.2 for the 350. Okay. Let's go to 400. So here's another 50 on here. And I wonder if I should start doing a half wavelength here. Maybe not. Okay, so like somewhere in this area is one node. So 2 node would be somewhere in this area. Maybe 150, I don't know, 155 and a half. 155.5. Why not? All right, so let's go to 450. Okay. And I think I might be better off to go to the first node and double it. So I kind of see it there, but let's see if we can get over here. Okay, about an 88. So maybe 84.2, and then double it. 84.2 would be a 16 and a 4.0, right? 84.4. Maybe we better check that. What I say, 84.2 times 2, 80. Did I say 84 or 82? 84. Okay, so let me fix that. So 168.4. All right, boom, nice. All right, so let's go to 500. And 500 would be throwing on another 50 here. And let's do the same thing here. See if we can kind of meet in the middle. Roughly it's an 88. So 88 times 2, 176, and I'll even put an O. Let's go to 550. So 550, nice amplitude here. 93.9 and double it. 93.9 times 2 is 187.8. And then finally to the 600. Should we call that a 97.3? 97.3 times 2 is 1.946. Good. All right, partner, you're getting all this. There's a lot of data for today. In fact, I didn't even say that at the beginning, but that's usually what I tell students is, hey, let me talk about the theory really quick because you guys have a lot of data to collect. Although I forgot to look at what time we started here, and I know we're not even close to our 3 hours, so we're way under the allotted time. All right, so let me go back now the other direction. Let's see, what was let me go to the 250. And so 250 would look like this. And I can hear it kind of hitting the meter stick. Okay. Looks like node 1 and node 2 is right here. And so maybe 123.5. 123.5. Let's go down now to the 200. And we'll do 150. So here's a 200. And maybe this needs a little more stabilizing. And these are the light ones again that jump around a little too much. Okay, and so there's node 1, and there's node 2. And so maybe call it 111 and a half, 111 and a half. All right, down to 150 here, and then here. Okay, let's see. Maybe we'll do a 96.8, 96.8. Okay, and then finally we're last one. We're at 100 grams here. All right, so last one. 100 grams. Node 1, node 2, maybe at about a 79 and a half. We'll just call it 79 and a half. Yay! Okay, I'll bring this close to the video. Although Ron said he was getting some good ones there, but maybe I'll just bring it close.
Hold on the table.
Oh, I'll hold it on the table and then just zoom in for a second, Ron, because they can pause it. So I'm going to tell you guys, as he zooms in, you can pause it, and you need to write all these down. Okay? And now, I'll disconnect all this, but let me jump over then to this graphical analysis, because now we can begin to analyze the data. And let me just show you what you guys need to do. I don't want to do too much of it, but I feel like I need to, since this is only the second lab, and there's a lot for you to learn here with graphical analysis. And like I said, a big thing that I want you to learn, of course, is the log-log plots, and the real advantage of them. That's kind of the conceptual side of the graphs in the lab. That's one of the big objective of this lab, and it's a follow-up of last time. But the other one here is just how do I make these multiple plots, and graphical analysis has some more advanced buttons that aren't so obvious that I feel I need to show you. Okay, so let me, this is from this morning. Remember I said that, so this is actually, for you guys, this would be last week's lab. Let me turn this off. Let me start graphical analysis all anew. Okay, and this is really for me to remind myself, I need to show you how to get to the virtual machine so you can start graphical analysis. So I'll make that video, like I said, tonight when I get home. But in your case, by the time you see this video, you should have already have done graphical analysis once. So go back to your virtual machine. Or if you guys prefer, you can use Excel or Google Sheets or any other one. It's just, I'm going to show you and give you the resources for graphical analysis. All right, so I'm going to go here to graphical analysis, and this will be your second time seeing it with me, and so that'll be good to kind of see the default here. And so let me begin by pointing out, remember the default gives me 2 columns, and this is your raw data, and so this would be the raw data. So let me do the light string first, and let me encourage you to put in all the information for the light string, because there's a button I want to show you, is that once you've done everything for one of them, you could just ask it to repeat itself. And so instead of setting this up 3 times for the 3 different strings, just do a full setup for one of the strings and then ask it to repeat. Watch, I'll demonstrate here. Okay, so the x-axis right here, I'm going to double click and change because I want that first one to be mass. So the full name is mass, the short name is M, and the units are in kilograms. So again, I'm going to put it in kilograms here, and I'll click done. And it looks like, I got to get my data table here, so this may take a little while to type. Looks like we got a 0.01, 0.02, 0.03, 0.04, and 0.05. So that's the first 5. It looks like then we go up by 50s. So after 50 grams, we have 100, 150, 200, 250, 300, 350, 400, 450, 500, 550, and finally 6. Let me just kind of double check those numbers, 10, 20, 30, 40, 50. 100, 150, 200, 250, 3, 350, 4, 450, 5, 550, 6. Okay, good. So I've got my masses in kilograms. All right, so now let's come over here and put in at least what we have. Okay, so we only are going to go to 250, but here is our wavelength. So it looks like 0.408, 0.596. Ooh. Thank you. 0.02. Oh, and I hit enter instead of arrow down. My bad. So enter makes it go to start over again on the first column. And I should have just done an arrow down. All right, so 0.08, 0.596, 0.722, arrow down, 0.828, arrow down, 0.928, arrow down, 1.320, arrow down, 1.582, 1.87, and 2.07, and that's all the data we have for the light string. Okay, all right. So I'll just stop right there. Now I probably should also change the title of it from the default Y to what it is. It is wave length. The short symbol is the Greek letter lambda. There is no Greek character in this one. It's kind of simple, so I'll just spell it out. However, you can do like a copy and paste. So you can go over to Microsoft Word, you can get a lambda, you can go in and paste. Sometimes that works, sometimes it doesn't. I forget which boxes that works for. But nonetheless, that's really not too important. The units here are meters, and I can click done. And so there it is. I've got a graph of wavelength and mass. That's not really what I want. That's what the default is. It always puts the second column on the vertical axis and the first column just to start, and we can change it. And that's what I showed you last time, and I want to show you some more of here. But that's the first 2 of our first measurements here. I'll As I said then, the rest of these 4 are going to be calculated ones. So let's make a column of tension. Okay, so just to remind you of last week, you may have forgotten, but under data, you can go new column. And you can either get one that you calculate yourself and type in, or one that the computer will type in as you calculates them. And that's the one I would want. So let's call this tension. And the symbol capital T. And the units are newtons. Okay. And the equation, and I'll just point it out here on the board again, was coming from Physics 121. Since there was no acceleration to our hanging mass, or at least very little, it was vibrating a little bit, but we'll call that 0. And then the tension would be equal to its weight, so the net force was 0. And anyways, it would just be its mass. And so if you remember us doing this last week, we just picked the column that said mass, then we picked the little shift 8 for the star, and then we multiplied by 9.8 and done. And let me just kind of make this table a little bigger so you can see. I now have 3 columns, and the first 2 are the raw data, and now there's a calculated one, which is the tension. Now, the other column right here, velocity, as I said earlier, comes from the wavelength times the frequency, and the frequency is set at a 60. So I'm going to essentially do the same thing. I'm going to come over here to data. I'm going to go new calculated column. I'll call this column the velocity. I will short name V. I will put it in units of meters per second, and here's that magical equation. That would be its wavelength. Now that's a column, so let me come over here to variables and choose the wavelength. There it is. And then the star again, the shift 8. And then times the frequency, which, as I said, since we plugged into the wall, in North America, it's 60 hertz. So there's the 60, and if I hit done, you will see it creates a 4th column. And of course, it only creates data where I have the data here, so it doesn't go all the way down. And of course, it's only up to here that I want to plot anyways for the first string. Okay. Now, as long as I'm here, let's make the other 2 columns. This one would be a calculated column. It's the log of the tension. So let me show you the same thing. Let me go to data. Let me go to new calculated column. I'll just call it log T, nothing fancy. Short name, don't really have a good idea. How about just LT? I'll do a capital T for log of tension. Let me hold off on the units. The units is an interesting discussion when it comes to logarithms that I better not get bogged down in. So I'll just go unit list for the moment and leave it alone. Okay, so let's go to that equation, and something that you haven't seen this semester. Half of you have seen it already, but there was this other button here called functions. Let me click on it. Because there's all kinds of mathematical functions. Trig functions, calculus functions. Of course, I'm going to be hunting right here for the log function. There it is. Under calculus, that's another menu, so I can have derivatives and integrals. Under trig functions would be things like your sines and your cosines. Exponentials, do I see exponential? Okay, there's exponential, or e to the x. There's natural log too. There's log and natural log. I was thinking about log base 10. We could do the same logic with a natural log base, but I've been thinking in my mind, and the author's saying that let's do log base 10 here. Okay, so I'm going to do log base 10, so I'm going to put log, and then of course log of tension. So I go to the other one that says variable, and there is log of tension. Now, as I said last time, and I'll say it again, as you get used to this, you might just want to type it out. You just got to know what the syntax is. So it would be a log, and it's a function, so you got to do the open and close parentheses, and then you got to do the variable tension, but you got to put it in double quotes. So you can type it, but I find it easier just to click on the function and the variable, and the computer takes care of all the syntax for me. But if I click done, And there it's given me the log of all these crazy things. All right, one more column. In fact, maybe I'll even open up my data table a little bit more so you can see all of them in one shot. Let me go to data, let me go to calculated column, and this would be the same thing. This would be the log, and this time it's log of velocity. So maybe for a short name I'll just do capital L and lowercase v. I'll skip the units. I'll jump down here and I'll choose the function again, log, and turn the variable velocity and click done. And there it is, my log of my velocity. All right, well, what is really important for me to show you and really cool about this program is this is all the information I have for the light string. And essentially I want to do the same thing for the heavy string and the medium string. So a nice little feature. Let me come to data again, and let me point out, it's right here. Instead of more columns, do you see this one up here that says new data set? So if you already have a data set, if you've already made a measurement, and in this case I have 2 columns that are raw data that I entered and 4 columns that are calculated, if I go new data set right here, I will get a whole new set of 6 columns with the same formulas. Oh, watch this. And so I can go, whoops, new data set. And for you to see everything, I have to expand this out. And it looks like it scrolled over. And so here is data set 1, and here is data set 2. And the formulas are already there. Okay? Now I guess that also kind of points out that I guess I didn't need to type all of these for this one because I'm not using them all. But if I'm not using them all, they won't, show up in my graph. So I don't think that's going to be a problem here. But watch this. What I can do is I can come over here under the mass, whoops, and just highlight it and copy and come over here and paste. And it will put all that mass in. And of course, remember the formulas are there, so it calculates the tension and it calculates the log of the tension. And of course, not a surprise, those are all the same numbers. So nothing is interesting too much about that other than just how easy it was. And that's one of the 2 big things I wanted to show you. Now, the other thing I need to do is then to type in these wavelengths, which only exists at the 40. So this would be the 0.455, 0.517, 0.722, 0.876, 1.016, 1.131, 1.243, 1.349, 1.424, and 1.522. So there's how I get the data all complete for data set number 2. Ah, now you see the idea. Watch this. I'm going to do the same thing. I'm going to go data, new data sets. And sure enough, and I can't even fit it all on this one screen, but there's the first part of data set number 3. Maybe I'll just scroll over so we can see all of 3 and all of 2, but we're losing part of 1. Let me highlight the mass, control copy. Let me come over here and do a control paste. Let me come back to where the data is relevant at 100 right here and type in the wavelength 0.795.968, and I'll pause for a second and say, look, this is what you need to do. So this is your role in our team. Okay, although right now I would say I'm not being the other partner with you, because if it was, you wouldn't have to do this. What I'm being is the teacher. And so now I got my teacher hat on and saying, look, this is what one of you, and it's you, have to do in order to complete the lab. So that's my teacher hat here. So if we were partners, I would just kind of email this to you and say, hey, here it is, already typed it in. But huh?
You can read this.
Oh, Ron was just saying it's more readable that way. Oh, good. Well, let me keep typing to kind of finish this up. 1.115, 1.235, 1.375. Of course, it may be more readable, Ron, but it has the potential of me doing a typo. Okay, hopefully I didn't. 1.462, 1.555, 1.684, 1.760, 1.876, 1.946. Okay, so I got a lot of data here. And so, like I said, with that additional effect that I can quickly create a whole new data set. I now have 18 columns. And that was a neat feature of graphical analysis I wanted you to see when we start collecting a lot of data. We didn't have to really kind of type everything when we ran the same experiment just 3 times. All right, so let me kind of close up the data table so I'm not looking at the whole thing. Maybe I'll just leave enough space that I can see 3 columns. Because you are asked to not only collect this data and type it in, but you are asked, and this is going to be what you're really turning in, to make a plot of all this stuff. Now, the first plot they ask, and I'll just show you with the red marker since I'm not sure what I did with my black marker, but they ask you to make a plot. Yeah, it's probably back here, but I'm just going to go with red. And is it pull? Should I go a little further over? Okay. So is to plot what I would call the old-fashioned plot. Let me take, we're done with this, so I can take this down if this is in the way. All right. So, and what I mean by the old-fashioned plot, and let me come way back over here, probably the kind of graph you were thinking, and the kind of graph you did in high school and middle school, the simple graph where your axes are simple, but your graph may be complex. So let's plot velocity versus tension. That's the connection we're trying to analyze here. So on the vertical axis, we have velocity, and the horizontal axis, we have the tension. Now, I'll rewrite the equation over here, but remember, the equation we're trying to see and prove if it is valid is this one, which is a square root function. And, of course, in addition to the square root of the tension, you have the square root of the mass density. So, who knows if this would look better? You could write this as 1 over the mass density times the square root of the tension. But the point is, if you just did your algebra from high school, you would say, well, this, if you plot tension versus the velocity, it should follow a square root pattern with a prefactor in front. Okay. So if I did all 3 of them, I guess I would expect to see equations that look like this. Now, I didn't give them the same tension, so I probably should modify this a little bit. But you see the one with the smaller mass density 1 over a small number is a big prefactor. So this would be the light string. And the light string would go from the small tension to maybe about there. Then the medium weight string, we didn't do the light tensions, and we did a little bit more here. And then the heavy weight string, we started about here and we went to a little bit higher tension. So that's kind of what I'm thinking I should see. And this is not as a useful graph as we ultimately want to see, but your author says plot this and print this and turn this in just to kind of give you that step from what you are more used to, where your axes are simple and your graph is complex, before we go to the next step, which is to make a complex axis and a simple graph. Okay, so let's see what we got here. So let me come over here and plot what they're asking for. And so on the horizontal axis, they are asking us to plot tension. And on the vertical axis, and let me go to more on this, because here's what I want you to see. I said to plot velocity. But there's 3 different strings. So what I mean by that is plot the velocity of each of them. And so this is one graph, but it's 3 plots. And so that's why you have to go to the more. I showed it to you last week that you can either just select one when you click on it once, but if you go to the more, you can check as many things as you want on that plot. So what I want to do is I want to check 3 things, and it's the velocity of each data set. So you can kind of see by default it has data set 1 and it has wavelength. But I really want velocity. So let me uncheck wavelength and put velocity. Let me expand data set 2 and check velocity in data set 2. Let me also expand data set number 3 and check velocity in number 3. And that's the second big thing I want to show you about graphical analysis. So not only is it easy to make all 18 columns, but we can actually put multiple plots on one graph, and sometimes that's really nice. And this is an example of that, where it's really nice to compare them, because we're really hoping to see this. And I'll say it again, even though we're going to even analyze this a little better, it would be really nice to see that they follow a square root pattern. They all 3 follow a square root pattern. The only difference between them is the prefactor. And you might even want to take a note of what the symbol is. Like data set number 3 is kind of this cyan color with a cross. And data set number 2 is kind of this green, puke green, and a triangle, an open triangle. And I won't bother to look at number 1. Now if I can just remember those 2, then I can kind of look at them. All right. So there it is, curving around. Are these backwards? Wasn't this the medium one? No, this must have been the, yeah, this must be the medium one. Why is the medium one a little below? Ooh, I might not have very good data. Did I mess up?
We just didn't know which one was the heavy string, which was the light.
Did I hook up the wrong string? Ooh. And they're very, very close. You know, and maybe that's my mistake, is one's nylon. It looked lighter to me, but it is pretty heavy. Oh, and actually, and this cotton looked, you know what? I think now that I hold them, yeah, this is actually pretty heavy. it's thinner, but it's heavy. It's got a nylon with a wax coating. Okay, my bad. I used the wrong strings. But maybe what's good is the data showed me that I messed up. I was tempted to redo it then, but you know, I kind of like this. And they're almost the same. And now that I feel them, this is definitely light, but yeah, these are, yeah, this is a thin, but it's dense. Okay. Well, it would have been a better lab if I had gotten these strings right. I do apologize here. But maybe this is kind of the fun thing. And that's actually where we're eventually going to get, is to get the densities of these. What I called the mediums, let me kind of fix this graph, is actually more dense than I anticipated. And it's almost the same as the heavy one from my data. And it actually looks like it's even a hair more. So I will learn a lesson here that string is really pretty dense. So let me call this the fake medium. Because it is not the medium. Although maybe I should look at a better graph. That's coming up here too. So let's see if this still follows along here. But before I print this, or I should say save it as a PDF, okay, put a connect the lines on these so you can see the pattern. We're not going to try to get any numbers from this graph because we're going to do a better graph. So this is our first graph. This is a graph that is trying to teach you the transition between a simple axis and a complex graph to a complex axis and a simple graph. So let me do one more thing, and I'm just going to double click in the center of the graph. This will bring up the graph options, and so I wanted to show you that, but I also wanted to say this button right here, this checkbox, which says connect the points. And if I do connect the points and go done, you can get a little better visual effect of the curve to it, and I think begin to see the square root function. So I'll say it again, it seems to be following a square root function. All right, so when you do all of this, this is your first graph and your first page to turn in. Okay, now for the grand finale here. So the grand finale here, as I was saying earlier on, is let's do this. Let's plot the log of the velocity versus the log of the tension. Now, I kind of talked about this math last week. I want to talk about it again in case you forgot. So let me clear this off. And say, let's take the log of this. So I would have the log of the velocity times the log of, and I'm going to go ahead and write the square root as a power of 1/2. Because as I was trying to say last week, and I think it needs to be repeated here, this is what Newton was thinking, that if you don't really know the mathematical equation of them, go ahead and do a log-log plot, because if it's raised to a power, you'll get a straight line. And then the slope and the intercept will give you useful information. So that's what I'm going to do. Now, the truth is, since your author derived it for you, I do know it's a square root, and we could do like we did last week, just square both sides, but let's go ahead and try the log-log idea. So this would be the log of the velocity. If I do the log roll, this comes out to be 1/2. Then it comes out to be the log of the tension over the mass density. Then this would be the log of the tension minus the log of the mass density. So again, using those properties of logarithms, when you have a quotient, you can subtract the two logs. If you remember last time I was saying this, I listed it as a product, so we added the two logs. Now we're subtracting the two logs. And then, of course, if you do the distributive property, you have 1/2 log T minus 1/2 log of mass density. And now you hopefully begin to see, and I'll repeat it, if you think about this as the y-axis, and you think about this as the x-axis, then this is the slope. Remember I said the power that it's raised to will become the slope when you do a log-log plot. And so let's see if we get graphs that have a slope of 1/2 for all three of them. Now, of course, this over here plus the b, this whole thing, including the negative sign, would be the intercept. And so I claim that if we do a log-log plot, and that's why we've done these columns, and you do a log-log plot, the slope and the intercept give you information. The slope tells you what power the tension is raised to, if you didn't already know. Of course, presumably we already know, so presumably we get a slope of 1/2. We'll see how good my data came out. And then, of course, the intercept would be related to the mass density, and so you're asked to find the mass density of each of these three strings. And so let's go ahead. And down here on the horizontal axis, put the log of the tension. And on the vertical axis, let's go to more again. And this time, instead of plotting the velocity, let's plot the log of the velocity for each of them. And probably need to do an auto scale. So far that's looking good. I have, as you hopefully can see, 3 parallel lines, right? They all should be raised to the same power. Now I have connect the lines on, but probably for this case, now that I have lines, probably better to turn that off and do the curve fit, because it'll put in the actual curve fit. And I usually don't want both, because then it just gets kind of confusing in there. So let me show you again how to turn on the connect the lines and off. I'll just double click on the graph. This time I'll turn them off, okay. And then I'll go, if you remember this regression line was up here, so I'll go regression line. And since we have more than one data set, we didn't get this last week. It's asking, you know, it's coming back and saying, well, which one of these data sets do you want to do with a regression line? Well, all of them in my case. So I'll put a checkbox by all 3 of them and click OK. And then maybe I'll just move my title boxes around and begin by looking at their slopes. Okay, so the lighter one right here should have a slope of about 1/2. Yay! I feel good. The other 2 should also have a slope very close to 1/2. Yay! I feel good. So all 3 of them are parallel. All 3 of them have a slope of 1/2. If I did not, and this is my main point, if I did not already know this over here, if I did not know that velocity was related to the square root of the tension, I have now just found it. I would have plotted it the first time and got these curves. Then I would have plotted the log-log, and then I would have saw their straight lines, and I would have got excited. This was the answer to the second discussion question last week, where it says, what graphing technique should you use if you don't know the relationship? And so the graphing technique is to first just plot the 2 things you're interested in and see what you have. And if it's a straight line, great, you're done. But if it's a curve, then the next thing is to do a log-log plot. And if you get a straight line, great, you're done. And that's what we have. Because anything that's a straight line in a log-log plot tells you it's raised to a power. So all you have to do is measure its slope. And then in this case, I would find out that the slope is 1/2, which means it's raised to a power of 1/2, which is the square root function. So that's how I would know the relationship between velocity and tension if I never had it. Isn't that beautiful? So that's the lesson. And I know you're not here in class face-to-face. I hope this remote learning is working for you. I don't know how excited you are, but I sure am. So thanks for the fun. All right. Now, I'm not quite done, because the other half of this, as I said, is the intercept. Okay? And the intercept here is a little harder mathematically. But this is saying that B is equal to -1/2 times the log of mu. And so you are asked to get a piece of paper, or you could put it on here. Now, if we're face-to-face, I usually tell the students to print this and then just do your math right on this and staple it together and turn it in the front. Since we're remote, I'm going to say it a little different. You should probably just save this as a PDF, and on another piece of paper or another window, just open Google Docs or Word or any word processor, and or write it by hand and then scan it or take a picture of it to turn it into a PDF. But I want you to find the mass density of our 3 strings. And again, I need to apologize. I did not pick a good medium string. Our medium is actually, according to our data, a little more dense. And you can see they're almost the same. But anyways, so my bad. We don't have a good light, medium, and heavy. We actually have a light and 2 heavies. Okay. But go ahead and find and do the math needed to get the mass density. Now, I'll help you a little bit with it, because I have noticed, even in a face-to-face setting, that students have struggled a little bit with this math. So watch this. Bring the 2 to the other side. Bring the negative to the other side. How do you undo a log? All right. What's the anti-log? It's raising to a power of 10. So 10 to the -2b is the mass density. So let's use our data. Let's use our graph. Let's find the intercept. Then let's get out our calculator and find the mass densities. So in this case, I would come over here and say, well, B is 1.9 here. Here it's 1.68 and 1.64. So again, you can see the intercepts of these two are very, very close. And so that tells me their mass densities are very, very close. But go ahead and do that calculation, because those are the things you're going to be turning in. I'll say it again. Turn in these 3 things. A graph, what I'll call the simple old school graph. Simple axis, complex function. But also turn in this. A complex axis, simple graph. Okay? And then show me these 3 calculations. Show me these 3 calculations for what is the mass density. And so if you make those 3 pages into a PDF, you can send it up by Sunday night, and that will be your learning lesson for the lab this week. And hopefully, not only did we learn a lot about graphical analysis and how to analyze data, but it also helped us with the classroom material with wavelengths and, wavelength times frequency is velocity, and that the velocity is related to the square root of tension, and you see that whole idea. That's really kind of the big thing. Now, I should say one more thing before I say we're done, and that is your textbook lists what the mass densities of these strings should be. Do not believe them. The reason they're wrong is those were the mass densities of the strings we had years ago. And this was our fault. When we wrote up the lab manual, My lab tech then wasn't Ron, it was somebody else called Don. I know they sound the same. But Don measured all those strings and he put them in there to see how close we could get. That was a mistake on our part. We didn't think ahead and say, well, we're going to run out of string someday and we're going to have to buy new string. And what are the odds that we're able to get the same type of string and we don't have the same type of string? So we should have never put it in there. And so just know that this is old data, okay? Your mass densities will not come out to these values. Also note that the ones listed are in grams per meter. You are doing things in kilograms. So do expect something like this, 0.001 kilogram per meter. That would be 1 gram per meter. That's probably somewhere around that heavy one. In fact, if I look at the data as the old heavy one was 1.24. So besides ignoring those numbers, don't get scared that your decimal places are way different. Those numbers are in grams per meter. You are measuring things in kilograms per meter. So again, this is probably something close to the heavy one, whereas the lighter one is under a gram. Now the numbers that's listed here for the lighter one is like 0.2. So our lighter one is probably something like this ballpark. So I'll say it again, don't take these as this is what you're supposed to get, but know that for the lighter one, you probably have 0.000 and then a number, and for the heavier one, you have 001 and some numbers, okay? And we don't have a medium one because I messed up on the string. So your two heavy ones are probably around here, and your lighter one's probably around there. All right, well, I hope that was a good second lab, and I know I enjoyed it. Even though my knees are a little sore from sliding around there on the floor, but interesting enough, it was kind of fun discovering that I grabbed the wrong string, and the data proved it. So with that, I will call it quits. Ron? Huh? And Ron said something about discussion questions. I don't believe this one has any, so let me just pause. Yeah, so no discussion questions this time. A lot of times there are, and but this one does not have any of them. All right, so I'm out for now, and good luck learning. Take care.